It's been 30 minutes. Where is this doctor?
I like cotton candy.
Man, this doctor's tripping. This doctor's tripping!
You have 2 days to live.
You're joking.
No, I'm just kidding. You actually have mitral stenosis.
Mitral stenosis?
Don't worry, John. Basically, your mitral valve is not able to fully open, causing the upper chamber of your heart valve to swell and lead to a buildup of pressure.
Mitral stenosis?
Don't worry, John. Over 2.5% of the American population is affected by valvular diseases. In fact, more than 105,000 people a year in the United States undergo heart valve replacement, and about 106,000 procedures are done every year. It looks like you're going to need surgery.
Doc, how long is this going to take? I'm a very busy man. I drive out to LA 4 times a week. I'm juggling 3 big contracts. I don't have time to just lay around all day.
Well, John, after your surgery, you're really going to need to take it easy for a few weeks. I think you're going to need an artificial heart valve to replace your current mitral valve. Although there are over 80 models of artificial heart valves, there are 2 general types, mechanical and bioprosthetic. Mechanical heart valves are typically composed of pyrolytic carbon, Dacron, Teflon, metal alloys, and Dalrand. Bioprosthetic heart valves are made of pig tissue and cow tissue.
Why do I need to know about all these materials?
Well, John, the materials are very important to the functions of each heart valve. Pyrolytic carbon, for example, is valued for its strength and ability to prevent clotting, while Dacron is good for its biocompatibility. Telron produces low levels of friction, while metal alloys contain corrosion-resistant properties, and Dalrand is valued for its long-term fatigue endurance.
So basically all these heart valves are the same, right?
No, John. There are 5 main types of heart valves right now: the cage wall valve, the tilting disc valve, the bileaflet valve, the xenograft valve, and the pericardial valve. For your case, I recommend the bileaflet valve, since it is more durable than the others and will last you for a long time.
You know what? No. Just no. I don't need this. Right? I can pick up my own heart valve. You don't even know what you're talking about. This hospital is run really poorly. I'm out of here.
Fine, just come back in 2 days and we'll schedule your surgery.
It looks like this heart valve works by letting fluid through in one direction, while flow in the opposite direction pushes the ball up against the cage and closes the valve. Okay, that's fine and dandy, but is this a pro or a con? The whole thing's made of a silicone elastomer with 2% barium sulfate, and then they sew the valve into the mitral orifice with a sewing ring made of knitted Teflon and polypropylene cloth. Now, this paper says these valves last for many years, up to 44, therefore lowering the need for multiple surgeries. But is that really a good thing? It's one of the first valves to be commercialized, so I'm sure something better's come along since then.
So this is the tilting disc valve. So far they've been pretty much as advertised, no surprises. This valve's got a tilting disc that opens and closes depending on the flow direction, and it does this 70 times per minute. That's impressive. And the disc itself is made of pyrolytic carbon and is restrained by 2 metallic struts. The valve is sewn into the orifice with knitted Teflon, like the ball and cage model. The whole thing is enclosed in a titanium cage. This one looks a bit better. The pyrolytic carbon in the disc is very biocompatible. The whole valve has the same problems as the ball and cage model did. It causes those blood clots, like Tom's doctor would tell me it's called thrombosis. And it looks like it causes orifice damage too. It doesn't even last as long, only 20 years? Although that is pretty long. Well, I'll look at other valves before Okay, would you please stop singing that?
Oh, I'm sorry. Maybe we prefer a different song. Like this one. It's Friday.
No,
Friday.
stop singing. Why don't you be useful instead? Tell me everything you know about the tilting disc heart valve.
What?
Yeah, that's what I thought. You don't know anything about the tilting disc heart valve. You don't even know that it's because it's made of an anti-corrosive metal like titanium that it's less likely to degrade in the body.
Hello?
And it's less likely to cause thrombosis than the ball and cage model. But it's still probably better types of valves that don't cause any thrombosis. So this still isn't the best model.
Fine, then don't use a damn heart valve. What?
Fine, I won't.
Okay then.
So this is the bileaflet heart valve. It has 2 leaflets, so it's basically the same as the tilting disc heart valve. No problem.
Professor.
What? What are you doing here? Lecture was canceled.
I'm here early because I'm studying for my OChem final tomorrow. And actually, the bileaflet and the tilting disc are only made out of the same material, but they're actually very different in function.
What?
Yeah. Bileaflet's design consists of 2 semicircular leaflets which pivots on hinges, and the 2 leaflets swings apart during opening, resulting in 3 separate flow areas. And the valves have stiff rings which strengthen the housing, and the housing of the valves include 2 round tabs called pivot guards that projects out from the inner side. And the inside surface of these tabs contain the butterfly-shaped indications that serves to retain the leaflets.
What?
Oh, and they are both made of pyrolytic carbons, which is very biocompatible and is a polycrystalline material that makes these valves susceptible to fatigue failure.
Oh yeah? So what does this mean for me? I mean a patient. What does this mean for a patient?
Well, are you asking, is it like the valve worth getting?
Yeah, is the valve worth getting for a patient?
Oh, I think so, because the valves last for a very long time because it's a mechanical rather than a biological, and so you don't have to replace it for a very long time. And the bileaflet systems has a really good flow mechanics, so it reduces blood clots during when you have the artificial valve. So probably it's the best type of mechanical valve in the market right now.
Are you even a business major?
I'm a double major in B&E and business. After college, I want to start my
Yeah,
own.
whatever. Just turn off the lights when you leave.
Good luck on your surgery. Hey, are you reading something on your Amazon Kindle 3?
No, because we're doing product placement. Go away.
Oh, please tell us what you're reading.
I'm reading about bioprosthetic heart valves. They're pretty obscure. I'm sure you've never heard of them.
Oh my gosh, Marissa, heart valves. Isn't that the club we went to last night?
Oh my god, Carissa. No, that's what we had for dinner last night.
No, silly, we had pork rinds for dinner.
Oh god. No. Shut up. Sit down. We're doing this. Alright, Clarissa. The xenograft heart valve contains bioprosthetic mitral valves that contain pig tissue. These valves contain flexible stents made of wire to reduce loading shock or stresses on critical areas of tissue and to enhance durability. The wires consist of an L-alloy or a cobalt nickel alloy. It's implanted into the annulus by a Teflon knitted ring. It is very durable and has good hemodynamics, which is the study of blood flow. However, mitral valve cryoprostheses deteriorate more rapidly to higher ventricular systolic pressures against the mitral cusp compared to the diastolic pressures resisted by aortic bioprosthetic leaflets. And Marissa, the Hancock MO2 is another type of bioprosthetic valve that is composed of pig tissue. It consists of a stent made of Delrin, which is a thermoplastic polymer that is manufactured through the polymerization of formaldehyde. It also has a sewing ring, reduced stent profile, and leaflets that are placed in glutaraldehyde at low pressure and for prolonged periods of high pressure. These leaflets are also treated with sodium potassium sulfate.
Leaflets? Like the one that grows on trees?
No. These bioprosthetic valves can cause potential paravalvular leaks and endocarditis inflammation. The durability of prosthetic valves is directly proportional to age, meaning that deterioration occurs rapidly within 3 months to 2 years of children and adults aged 35 to 40. However, these valves require no lifelong anticoagulant therapy, inexpensive, and is mass-produced. Now you can both stop being so ignorant about at least one thing.
Produce? Like oranges?
Wow, you're really smart. I bet you can buy it in your head.
Yeah, you remember that without even reading it.
Now, like I know about all the stuff about prostate, bioprosthetic valves or anything, you know?
Sure.
Hey, do you want to get some coffee or something?
Yeah.
No, I need to get going. I usually stop by ultra convenience cafes and make something.
Whatever.
So I see you're back.
Doctor, I know it was a bit rash during our last meeting, but I really need your expert opinion. Did some research on the biomaterials myself, but I don't have a thorough understanding of all the materials and everything, so I could really use your input.
Okay, well, I actually have some research on biomaterials right here.
It's really handy.
As I mentioned earlier, there are two types of heart valves, mechanical and bioprosthetic. It is important to talk about the pros and cons of each material before deciding which device you want.
I see.
Mechanical heart valves are made of metal alloys such as stainless steel and titanium, which are strong materials and are less prone to corrosion. Usually they are coated with pyrolytic carbon, which is durable and allows the device to remain functional for a longer period of time. Unfortunately, mechanical valves are not biocompatible and will induce thrombosis. Although there has not been a discovery of a thrombogenic material, there has been research done on thromboresistant materials, such as pyrolytic carbon. Although blood clotting will still occur, it will be at a slower rate.
That's good.
In order to attach the device at the appropriate site, we make use of the suture ring, which is made of Teflon. This material doesn't create much friction, but it is not as resistant to wear as Delrin. Although Delrin is more wear resistant, it could obstruct the valve. It could cause the valve to deform and obstruct it.
Doctor, when I was doing my research, I came across this material called Dacron. Could you tell me more about that?
Yes. Dacron is used as well, but it is attracted to valve molecules and has the tendency to absorb them. This could reduce the strength of the material through the manufacturing process. Research is still being done.
Doc, could you tell me more about the bioprosthetic heart valves?
Yes. Biological valves are more biocompatible than mechanical valves because they are made of pig and cow tissue. However, they do calcify and deteriorate faster.
Okay, doctor, based on what you told me just now, I'm going to get the bileaflet heart valve because I don't want a lot of surgeries and I want it to last for a really long time.
Okay.
What a new guy.
Okay, I'm here. I'm going to get started right away. Okay. My name is John Medici, and I've come to talk to you guys today about a new way forward. I want to talk to you today about artificial heart valves. The artificial heart valve market is expected to reach $700 million by 2010, and when the facts come out in a year or two, we'll see how true that is, but it's a pretty big market. It's projected to reach $1.3 billion by 2017, and this is just in America, this isn't counting Europe or developing countries. It's expected to take approximately 4 years before a new device is recognized on the market, so that's why we need to start now and get into this market quickly so that when it does reach this size, we're in the middle of it. Okay, so there's two kinds of heart valves. There's mechanical heart valves and bioprosthetic heart valves. Mechanical heart valves have pros and cons like everything else. They don't wear out easily. Great coating for metal alloys. We use pyrolytic carbon, which decreases the chance of blood clots. We use Teflon, which has low coefficient of friction and low surface energy. Cons though, patients have to take blood thinners for life. It's a long time, that's 40 years in some cases. They're not as biocompatible as bioprosthetic heart valves, and they use Delrin, which is hydrophilic, absorbs moisture, and can cause obstruction to the valve. Bioprosthetic heart valves are good because they mimic the heart's natural valves and they're biocompatible. They're made out of pig or cow tissue usually. Their cons though are they get calcified, which means they harden and they stop working. This stiffens the leaflets and there's faster deterioration. There's ways to improve the biomaterials, which is why I'm here to talk to you guys today in your biomaterial company. Currently we use pyrolytic carbon. What I would like to develop is an implanted drug patch with blood thinning medication that locally releases blood thinners just around the heart valve instead of forcing the entire patient to use lots of blood thinners over their lifetime. We can coat the metal alloys in order to create thrombo-resistant properties and increase durability. For PET, also known as Dacron, we need to make it more resistant to wear than Teflon. And for the pig cow tissues and bioprosthetic heart valves, I'd like us to use GAG stabilization, which can improve durability of bioprosthetic valves. For cutting-edge research, we're going to use self-anchoring sutureless valve that is a new aortic heart valve prosthetic that increases the ease and speed of procedures and improves the hemodynamic characteristics of the valve. We're going to use a two-part bioprosthetic tissue valve that incorporates both mechanical and bioprosthetic heart valves and will provide maximal patient benefits. And we're going to use the semi-rigid angioplasty ring, which has shape memory and superelastic core that mimics 3D motion of the annulus.
But John, our company has never made medical devices before. There's so much paperwork and regulations we have to deal with. We might have to hire a whole new legal team.
You're right. One of the problems with this market is the FDA approval, which is just a load of red tape. However, it can be managed and we can make a profit on this. Class 1 products have the least regulatory control and are most exempt from pre-marketing notification and compliance with good manufacturing practices and regulation. This is like stethoscopes and stuff. I mean, you're not going to kill someone with a stethoscope, right? Class 2 is like X-ray systems. Those require pre-marketing notification and FDA review of a clearance to market submission. But what we're making is heart valves, and those are Class 3 products. It's the most rigorous regulatory control, requires pre-marketing approval and FDA market submission. As you can see, we've found a flow chart of the FDA process, and you can take your medical device and follow the flow chart all the way to the regulatory goal. The FDA process for us is going to be step 1. FDA collects existing information. And then step 2, the FDA assesses the risks and benefits of our device. In step 3, they propose classification into class 1, 2, or 3. We're going to be in class 3. And in step 4, the FDA receives and reviews comments. In step 5, they finalize the classification. So what we're going to do is we're going to turn in our product, we're going to go through all these steps, and at the end of it, they're going to say, company, you have a class 3 heart valve.
I'll discuss this with my committee and we'll get back to you.
Thank you for your time. Oh, one more thing. Turn up my heart when I'm with you.
You're apart, I feel it too.
And no matter what I do, I feel the pain. Without you.
Boom, 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 boom. Boom.